This meeting is being recorded.
In section 2.11, we're going to review which resonance structures will actually contribute to the actual structure of a molecule. And we know that when we draw multiple resonance structures, the actual molecule is a blend or a hybrid of all of these resonance structures. But not all of these resonance structures will contribute equally to the hybrid. So we're going to learn some rules and determine how to list the order of importance of these resonance structures. So just because it's a valid resonance structure because it doesn't break the octet rule or the don't break a single bond rule, it may not actually contribute to the hybrid structure. So let's take a look at these rules. So rule number 1 is that the most significant resonance forms will have all atoms with filled octets, right? So that would be the greatest number, all atoms. So always look and see if all of the atoms in your Lewis structure have a full octet. So over here, we'll start on the left. So we know that hydrogens, they only need a duet. So let's take a look at carbon here. Carbon has 3 bonds to hydrogen, 1 to oxygen. That has a full octet. Our central oxygen has 2 bonds, 2 lone pairs. Also good, full octet. Hydrogen's good. These 3 are good. Carbon has 3 bonds to hydrogen, 1 to another carbon, so that's okay. This carbon here only has 3 bonds. So that has does not have a full octet. Whereas if we move that lone pair from the oxygen, we still have a formal charge over here on the right side here of this resonance structure. But since we move that lone pair, now the double bond between the oxygen and carbon gives this carbon a full octet, and this oxygen still has a full octet, even though it has a formal charge. So this structure on the right would be more significant and would be more of a major contributor to the resonance structure. So let's take a look when we have 3 resonance structures in this scenario. So rule number 2 tells us that the fewer number of formal charges is more significant. So let's take a look without ranking anything yet. All right, we have no formal charge here, and then we have 2 versus 2 over here, right? This nitrogen and then this carbon, right? So we have no formal charges in the first structure. So that automatically would make us think that it is the most significant, right? And the first 2 structures then, we also want to always check for octets first. So we assume that we did that, but let's go back. So the first structure, we have a full octet. We know carbon wants 4 bonds, nitrogen wants 3 bonds and 1 lone pair. All the hydrogens look good. So the first molecule is the most significant, not only because it has a full octet, but it has the least amount of formal charges. Molecule 2 is more significant than resonance structure 2 is more significant than resonance structure 3 because resonance structure 3, there's not a full octet on that carbon. But in this carbon over here, we still have a positive and negative formal charge, but overall in the molecule, but the carbon has a full octet in this case. So we would rank them 1, 2, and 3 in this manner. Next, we have an example here that shows us when we have an overall formal charge, we want to focus on the resonance structures that show delocalization of the charge the best. So we have 2 negative formal charges, 2 negative ones on each oxygen or on 2 oxygens in each of these structures. Over here, we have way more formal charges. We have less even distribution of positive and negative charge. So that's what they mean about the delocalization of charge. So out of these 4 possible resonance structures that we could draw for this carbonate ion, right, CO3, 2 negative, we would say that only these three would be major contributors, and they are all equivalent contributors because they all show the same number of atoms with a full octet and the same overall delocalization and distribution of formal charge. So in rule number 3 now, this is the next rule. We look at the negative charges specifically. They would be on the more electronegative atom. So let's look at our first example here. We have a -1 formal charge on an oxygen up here. So 3 lone pairs, 1 bonding pair, and then over here we have 3 bonding pairs, 1 lone pair on a carbon. So carbon is less electronegative than oxygen, so that's why this structure is less significant. In our second example down here, we see the reverse. We see a +1 charge on a more electronegative atom, right? So we mentioned the negative charge on the more electronegative atom is preferred. The positive charge will be on the less electronegative atom. So oxygen's more electronegative than nitrogen in this case, right? So that positive charge on the nitrogen would be our more significant structure. So let's take a look at this problem here and see if we can draw the significant resonance structures that would result here. So we know this nitrogen with a negative charge and only 2 bonds would have 2 lone pairs. So they're not indicated here. So in this first structure that I have, I can move this lone pair here, but then that carbon atom at the bottom there would then have 5 pairs. So what that means are 5 bonds or 4 bonds in a lone pair. So what we have here is to move these pi electrons to this carbon atom here. So I'm going to draw some resonance structures here. So we would end up with NH up here, a double bond now to that carbon atom. This pi bond has broken, and we end up with a lone pair there. All right, so this would be our first resonance structure for this molecule. And then, let me go back, we'll switch colors back and forth. So now I'm going to draw my arrows. So I have a lone pair, right? That's allylic here. So I can move that here, and then I can take my double bond and move that pair there. So that movement would result in this molecule. Oh, I forgot the lone pair on nitrogen. Didn't go anywhere. So here's our second structure that would result, our second resonance structure that we could draw. So I moved around. That lone pair became this double bond. Here, the lone pair was placed down here now from the double bond, the second double bond. And then over here, we still have that lone double bond from before, right? We have our hydrogen there. That didn't go anywhere, nor did the lone pair up top. All right, so now I'm going to grab one more color, and we'll move around some electrons here. So now we're going to take this lone pair, move them there, take this double bond, move those electrons there. And let's see what results now. So again, nitrogen with hydrogen, everything remained the same. We moved the lone pair on the bottom to form a double bond over here. And then that double bond on the right, those pi electrons were moved to form a lone pair here. And we have to indicate our negative charges, right? So let's go back and make sure we do that in all of these structures. So each of these carbon atoms that I drew this negative sign next to would have a -1 formal charge. And all 3 of these resonance structures would be equivalent, right? Because we follow the rules, each of which all the atoms have a full octet. We also see an even distribution of that formal charge. So we will continue with our last section from chapter 2 next time.